All right, so here's an example of Snell's law where the light ray goes from air into glass and then into water. So something like a fish tank, as stated in the problem there. Okay, so we have a light ray that's going from air and then it hits the normal at about 35 degrees. And then we have to figure out for part A what theta 3 is, which is in water, and then it wants us to figure out the speed of the light in glass and then the speed of light in water. So the first strategy is to take it from air to glass and then from glass to water. So I'll baby step it for you, and then I'll show you how to do this by bypassing um, glass. So here's the first line, the red dashed line that comes up. That is your new normal line, where the ray hits the glass, where the interface between glass and air. So that's your new normal line, and that line should be drawn perpendicular to the surface. In this case, where my cursor is, that'll be the surface of the glass in which the air is striking it. And then from there, we know that it goes from air to glass, and glass has a higher index of refraction. So the light should bend towards the normal a little bit. I did my best to kind of draw it as such, where it's not just going straight through, but it does veer left, in this case, towards the normal just a little bit. And then that would be your new angle theta 2. And it's important to keep in mind that the angle in Snell's law should always be touching the normal line. So for example, this 35 degrees down here that's given is already touching this dash normal line, the imagined normal line. And therefore, it's important to kind of reference the normal line. Otherwise, your answer is going to be off. So that'll be theta 2 in my work here in red that just came up on the screen. And then the new blue dash line, that is quote unquote your new normal line between the interface of glass and water. So every time it strikes a new boundary, it's a good idea to just draw the new normal line where the beam strikes the surface. That way it's just easier to reference your angle. Again, as you can see, the blue dash line there, that's my quote unquote imaginary normal line. And then this is where the water is now present. Okay. And then since it's going to go from glass, which is more dense, into water that's a little less dense, it's going to veer away from the normal line. So I've drawn the blue here kind of veering to the right a little bit away from the normal line. So keep those concepts in mind. And this would be our theta 3. So we have theta 1, which is given to us 35. We need to know theta 2. And then finally, it's asking us to find theta 3, which is in water. So all you have to do is set up Snell's law. Pretty straightforward. So according to Snell, there's the index refraction of the medium 1, the angle, again, theta 1 touching the normal line, and index refraction 2, in this case, it'll be glass, and then sine of theta 2, which is also glass. And there's a lot of information known already, so a lot of the work now is going to be plug and chug. So to find theta 2, we first divide both sides by n2. As you see in my work there, n2 got divided, so we'll just move to the denominator on the left side there of the function. And then to find theta 2, we'll go ahead and plug in all the stuff that we know. The index refraction for air is 1, the given angle down here, where it first strikes the surface, the interface between air and glass, is 35 degrees. And then it's given that the index refraction for glass is 1.5. So if we just do a little basic calculator work, the left side reduces down to 0.382. And then to find theta 2, you would just have to take the inverse in order to find theta 2. And if you do that correctly, the angle comes out to be about 22.48 degrees. So this angle here in the diagram, theta 2, is about 22.48 degrees, which makes sense. Again, because it is going from less dense to more dense, this angle has to be a little smaller because it is veering towards the normal line. That's one way to check to see if your answer makes sense. And then the next step would be to go from glass to water. Pretty much exactly the same process, except now we just substitute different values in, since we're going from glass to water. And ultimately, part A asks us to find theta 3, which is the refracted angle in water. Okay, so instead of starting from air, we just start from glass to water. And then we know a bunch of stuff already. N2 is given us 1.5, theta 2, which is calculated in the previous steps. And then N3 is given as 1.33 in the schematic there, the index refraction for water. So if we do just a quick basic substitution, theta 2, we just found is 22.48 degrees. If we plug that in, everything's pretty much known. And then you get this result. And again, to find theta 3, you do inverse the sine of 0.43, which is what I have on the screen. And ultimately, you get an answer of about 25.5 degrees. Again, give take a take a little bit of a rounding error, but about 25.5 degrees. Okay, so that'll be your answer for part A. Now, the shortcut would be to bypass this medium glass. According to Snell's law, it should work out because this middleman is unnecessary. A lot of kids will do this step by step. I like to encourage you, if you understand substitution, just go ahead and substitute it out. So the first statement up here is n1 sine 1 equals n2 sine 2. I just carry that down here. And then as you can see on the right side, you also have the same statement, n2 sine 2, which is equal to n3 sine 3. So if you kind of notice here in red, both these statements are the same. So we can go ahead and set the first medium equal to the third medium because it does equal to these two terms. And anytime things are equal in physics or math, we just go ahead and set them equal to each other. So you have this statement. And keep in mind for part A, you're solving for theta 3. So again, a little bit of algebra manipulation. You should get this function dividing both sides by n3. And then if you substitute all your knowns in, you should get the same answer. N1, again, being air. The incident angle from air to glass is 35 degrees. And here, instead of using glass, we just bypassed it. So we'll just go ahead and go straight to water, which is 1.33. And if you do that, you can just trust me on the calculator work. It does come out to be the same angle. Okay, so theta 3 would be 25.5. I encourage you to do this second strategy because it does save a little bit of time. But whatever you're comfortable with, if you want to go from one medium to the next and then from that next medium to the third medium, that's up to you. All right, for part B, it asks what is the speed of the light ray in glass. The easiest way to do this is just using the index of refraction function, and that is the index of refraction equal to the speed of light in a vacuum divided by the speed of light in that new medium. So to manipulate the function to solve for v, because the question does ask for speed, so we'll go ahead and multiply both sides by v and then divide both sides by n. So v is equal to c, which is the speed of light in a vacuum divided by the index of refraction. In this case, the index of refraction would be for glass, and part B wants us to know the speed of light in glass. So I went ahead and add subscript here to your v, so it'll be v glass is equal to c. C does not have a subscript because that is the speed of light in a vacuum, which is essentially the speed of light in air. Okay, the difference is very minimal, so we just went ahead and assume that C in air is also the same as it is in a vacuum. And everything else is given to you, so this is just plug and chuck now. The speed of light in a vacuum or in air is 3.0 times 10 to the 8 meters per second. The index of refraction for glass is given in the schematic here as 1.5. And calculated work time should yield 2.0 times 10 to the 8 meters per second. So that's your answer for part B. The alternative way to do it, which I don't recommend, but this is just to show you the relationship between Snell's law and the index of refraction function here. Again, if you want to bust out Snell's law, you have that. And then we know from this function that the index of refraction is C over V. So C over V. But here C doesn't have a subscript because C is just a constant, a universal constant. V would be the speed of light in the first medium. And then again, you can substitute N2 out for the same function, which is C, but in this case, it'll be V2. It is N2. And then you notice here, C and C appears on both sides, and you're just multiplying and dividing. So you can go ahead and cancel that out. Canceling out C will leave you with just a coefficient of 1 on the top. And then to make this function, instead of having fractions, I would just multiply both sides by V2. And then again, do the same here where I can just move V1 up there or multiply both sides by V1. And it will look like this. The subscript here is going to be a little different, where it's V2 theta 1 and then V1 theta 2. So keep that in mind just in case you're memorizing the stuff. It's important to memorize the order of the subscripts here. Otherwise, you will screw yourself over. Okay. Other than that, though, to find the speed of the light in glass, in this case, that'll be V2. We can go ahead and isolate for V2 by dividing both sides by sine theta 1. And then everything else is pretty much known. Again, medium 1, V1 is just speed of light in air, aka a vacuum. And then theta 2 we found for in part A, which is 22.48. And then the angle of incident from air, according to this diagram here where my cursor is 35 degrees. There's no tricks to this question. It's pretty straightforward. And you should get this particular answer, which is the same. So as you can see, there's two different ways to do it. Actually, there's more than 2 ways to do it, but I would just say do the left strategy if you know the index of refraction function. Otherwise, if you know Snell's law, you can kind of wiggle your way through and it should yield the same outcome. All right, good luck. Don't be whack. Stay nerdy.